Poetry, and just lyrics to music more generally, are composed of lines of lyrics. Typically, especially in popular music, these lines are written to have some sort of rhyming structure. The structure is what we call a rhyme scheme, and is often represented by a sequence of uppercase letters. For example, a 4-line poem or 4 lines of lyrics could have an A rhyme scheme. This means that every line ends in the same sound, and thus all 4 of the lines rhyme. They could all end in the O sound, like go, flow, bow. They could all end in the A sound, like say, day, stay. Or here's an example I made up. Night before the test, I hit the desk and I cram. Since before I was 10, I've been destroying exams. My brain moves so fast, might find machine in the man. Me and the stoners both just want to sell some more of the gram. In this example, all 4 lines end with an am or an sound. That one's technically a slant rhyme, but for the purpose of the rhyme scheme, it's still just A. Of course, usually more than a single sound is going to be involved in the rhyme scheme, and so you might get a rhyme scheme like A, B. This means the first and third lines rhyme, and the second and fourth lines rhyme. Of course, especially in hip-hop music, there may be many rhymes inserted in the interior of the lines, not just at the ends, but just considering the ending rhyme schemes, it's clear there are a lot of different possibilities. But in a short poem with 4 lines, or more generally any number of lines, how could we possibly count the total number of possible rhyme schemes? Well, it may be helpful to first just knock out some simple cases. Of course, the more lines we have, the more possibilities there are. Let's say the number of lines is n, and consider the case where there are 0 lines. Then the total number of rhyme schemes, what we might call r, we can agree to call that 1. There's only one rhyme scheme, which is no rhymes at all, because there are no lines with which to rhyme. On the other hand, if there is a single line, well, still there is just one rhyme scheme, which is to have no rhymes at all, because if there's only one line, there are no other lines with which to form a rhyme. If we have 2 lines, then finally rhyming actually becomes possible, but the rhyme schemes are still very easy to count. Indeed, in the case of 2 lines, the possibilities are this. Either the 2 lines don't rhyme, so it would be an A-B scheme, or it's a rhyming couplet, and it would be A-A. The 2 lines do rhyme. So in the 2-line case, either they rhyme or they don't. There are 2 possibilities. After this, it starts to become a bit less trivial to count these things. I mean, in the 4-line cases we looked at, we only considered a maximum of 2 rhyming sounds, but with 4 lines to work with, it could be that none of the lines rhyme, and we have an A, B, C, D scheme. There are just bunches of possibilities here. The numbers, though, at this point are still small enough that we could count them without exercising a great deal of care. We just have to be a little bit organized in our work. However, to count the number of rhyme schemes with 3 lines, I am going to be very clever and very careful, because the method we're going to use can be generalized to count rhyme schemes for any number of lines. So let's wrap our heads around this clever counting method for 3 lines, and then we'll really get a good idea of the mathematics at play in counting rhyme schemes. So right now we're considering the case where we have 3 lines. Let's call these lines L1, L2, and L3. To count the number of rhyme scheme possibilities on 3 lines, let's focus our attention on L1 and how it could relate to the rest of the stanza, let's say. One possibility is that first line, L1, rhymes with none of the other 2 lines. In this case, the only rhyming possibilities exist between the other 2 lines, lines 2 and 3, and we already know that if we're considering 2 lines, there are 2 rhyme schemes. Thus, in this case, where line 1 doesn't rhyme with anything, that contributes 2 to the total number of rhyme schemes. Because again, if L1 doesn't rhyme with anything, the only scheming there is to be done is between L2 L2 and L3, and we know that gives us two possibilities. Either they rhyme with each other or they don't. The next possibility would be that L1 rhymes with one of the other two lines. Now, whichever line L1 rhymes with, in this case, that leaves one other line standing on its own, and we know that in the one-line case, there's only one rhyme scheme. So in the case where L1 rhymes with one line, the total number of additional rhyme schemes is just the number of ways that this can happen. How many ways can L1 rhyme with a single line? Well, it's just the number of ways that we could pick a single line for it to rhyme with. In this case, we know that number of ways is 2. It could rhyme with L2 or L3. There are two options, but there is mathematical notation for this, which I'm going to use here just because it's going to be critical to use this in the more general case. The notation is called a binomial coefficient, and it looks like this. This is read as 2 choose 1. It's the number of ways of choosing a single line for L1 to rhyme with out of those two lines that we have as options. 2 choose 1, of course this is equal to 2. So this is the total number of additional possibilities, which is equal to 2. To be more explicit about the possibilities here, it could be AAB, so L1 and L2 rhyme and L3 doesn't, or it could be ABA, so L1 and L3 rhyme, but L2 does not. The last possibility, of course, is that L1 rhymes with both of the other two lines. This would mean that among those other two lines, we have to pick two of them for L1 to rhyme with. The number of ways of picking two lines from a collection of two lines is, of course, just equal to 1. So this adds one additional possibility. So we see in total for 3 lines, there are 2, 4, 5 total rhyme schemes. Now, there is a little bit more to this than meets the eye. However, you can't really see it just because the numbers involved here are so small. We'll be able to see what's going on in full when we look at the n equals 4 case. But first, it's probably a good idea to talk a little bit about the mathematical jargon that this relates to. Let's just fill in that last piece of information in our table here. For 3 lines, we counted there are 5 possible rhyme schemes. If we can agree for a moment to use some less cumbersome notation, let's just call the 3 lines, still discussing that case, but now with a more mathematical perspective. Let's call those lines 1, 2, and 3. And here I've put them in what's called a set. These are set brackets. So this is a set containing 3 objects, in our case 3 lines of poetry, and what we've just counted is actually the number of ways to partition this set. A partition of a set is a way of taking the elements of the set and putting them into separate parts. In the context of music lyrics, these parts are rhyming sounds at the end of a line. One possible partition would be to put all elements of the set in their own part. They all get a separate part, and that would look like this. In the context of lyrics, these are 3 lines which all end in different sounds. This is an ABC rhyme scheme. And of course, just like a line of poetry can only end in a single sound, an element of a set can only be in one part of its partition. Another partition would be to have 1 and 2 in the same part, but 3 separate. That would look like this. We have 1 and 2 together, and 3 is separate. This would be an A-A-B rhyme scheme. Lines 1 and 2 rhyme, and the third line doesn't. Of course, another possibility would be to rhyme lines 2 and 3, so they could be in their own part with 1 separate. That looks like this, and the other 2 possible partitions, or rhyme schemes, look like this. This one here, for example, would be an A-B-A rhyme scheme. And of course, all 3 of the lines could rhyme, which mean they're all in the same part. In this view, all of the lines that are in the same part are equivalent in the way that they end in the same sound. Just like in the context of numbers, we might say 6 and 10 are equivalent because they're both even. However, in a different context, they might not be equivalent. Of course, they're not equal numbers, for example. Just like 2 rhyming lines of poetry might have a different number of syllables, and so they could be equivalent in one respect, but not in another. Now, in this example, I've put the numbers 1, 2, and 3 in the set, but of course, in general, it doesn't matter what 3 distinct objects are in this set. As long as they are 3 distinct objects, the number of ways to partition them is 5. Some more useful notation on this topic involves square brackets. If I put 1 in square brackets, this is a shorthand for the set that contains 1. Similarly, Similarly, I could put the number 2 in square brackets, and this is the set that contains 1 and 2. This set that we've written up here could be written more shortly as 3 in square brackets. More generally, if we have n in square brackets, this is representing the set of the first n positive integers. Now, the numbers we've been looking at so far, like for example 5 partitions of this set of 3 objects, that's what's called a Bell number. These are denoted Bn, and they were named after beloved mathematician and author Eric Temple Bell. Although over 30 years prior to E.T. Bell publishing about Bell numbers, Ramanujan had written about them in chapter 3 of his second notebook, so it's a little surprising they don't bear his name instead. To quickly tie this notation back to what we've discussed so far, these R values are actually the first few Bell numbers. So here where n equals 0, well, like we've just said, that would actually be B0. Here where n equals 1, this is B1. N equals 2, this is B2, and so on. The Bell number Bn is the number of partitions of n distinct objects, and as we've seen, that is also used to count the number of rhyme schemes on a stanza consisting of n lines. Now, the number of rhyme schemes for a stanza with n lines is actually gargantuan just for medium-sized n values. For example, in hip-hop, a traditional verse consists of 16 bars, where bar is just another word for line. And for 16 bars, the number of rhyme schemes, I don't know it right now offhand, but it's absolutely massive. Before we even think about computing B16, we probably should find some more mathematical machinery with which to do it. And for that, let me just give you one more quick piece of notation. In case you need a review on sigma notation, this is a notation that's just used to add up a bunch of stuff. For example, if I write this sigma with k equals 0 on the bottom, 5 on top, and 2k next to the sigma, this is just telling me to add up 2 times k for all values of k from 0 to 5, where k is taking on integer values. So this would be 2 times 0, the first value of k, plus 2 times 1, the next value of k, and so on, all the way up to k equals 5. If you run the numbers, this is 30. Alright, with that said, I'm prepared to show you what's called a recursive formula for the Bell numbers, which is exactly the sort of calculation that we were doing before. So yeah, sad to say, we're not just getting a real nice, short, and snappy formula for computing Bell numbers or the rhyme schemes on n lines. So this is the formula, and you may notice that the previous Bell numbers occur when you're trying to calculate a new Bell number. To find Bn plus 1, I need to know all of the other Bell numbers from B0 up through Bn. This is called a recursive formula because the previous Bell numbers recur each time you're trying to calculate a new Bell number. I'm not going to do a rigorous derivation of this formula, but let's go through these calculations again with n equals 4, so a 4-line poem, and I think that will be enough to convince you of the truth of this formula. So again, we have 4 lines, which we're going to call L1, L2, L3, and L4. And again, we're going to fixate on line 1 and look at the different possibilities of how line 1 could fit into the rhyme scheme. Of course, it's possible that line 1 rhymes with 0 other lines. In that case, among the other 3 lines, we get to choose 0 of them for line 1 to rhyme with, and 3 choose 0. We say that's just 1. There's one way to choose nothing from a collection of 3 things, which is to just choose nothing. Now, once we've chosen the 0 lines that L1 will rhyme with, of course, in this case it's trivial, we're not picking anything at all, there are 3 lines left that can have whatever rhyme scheme they please. And how many rhyme schemes are there for 3 lines? Well, of course, that's the Bell number B3. So this contributes 3 choose 0 times B3 possible rhyme schemes, and we'll plug in the actual numbers once we're done. Again, this 3 choose 0 is just 1, it's not really doing anything. I'm putting it here though so you can see where this summation is coming from. So moving on to the next possibility, which will fit into this form a little bit more naturally, L1 could rhyme with 1 other line. In that case, among the other 3 lines, we have to pick 1 for L1 to rhyme with, and there are 3 choose 1 ways that we could do that. Now, whichever line we pick for L1 to rhyme with, that leaves 2 other lines, and there are B2 ways that those lines could have a rhyme scheme. So for every one of the 3 lines we could pick L1 to rhyme with, the other 2 lines have B2 possible rhyme schemes, so this is the total number of additional contributions from this situation. Only 2 possibilities left to knock out, which I think you'll be able to understand pretty quickly. L1 could rhyme with 2 lines. In that case, there are 3 other lines, and we need to pick 2 of them for L1 to rhyme with, so that's 3 choose 2 possibilities. Whichever 2 lines we pick for L1 to rhyme with, that leaves a single line by itself, and a single line has B1 possible rhyme schemes. The final possibility is where line 1 rhymes with all of the other 3 lines, in which case we have 3 lines to choose from and we have to pick 3 of them for L1 to rhyme with, which leaves 0 lines behind, and 0 lines have a total of B0 possible rhyme schemes. And now you can probably see where this formula is coming from. These computations are trying to find B4, the 4th Bell number. So in that case, n is equal to 3. So up here would be n equals 3, and we would start with k equals 0. So of course, this Bell number is B3 minus 0, or B3, just like we see here. The next one would be when k equals 1, which is B3 minus 1, or B2. Then B3 minus 2, which is B1, and so on. Now you may notice the binomial coefficients here are going in the opposite order of what we've written. When k equals 0, this would be 3 choose 3 minus 0, or 3 choose 3. And then it would be 3 choose 3 minus 1, or 3 choose 2, and so on. But the binomial coefficients have a symmetry to them, so that doesn't really matter. 3 choose 0 is the same as 3 choose 3. 3 choose 1 is the same as 3 choose 2. So there are perhaps some nicer ways we could write this formula. We could write it like this, which is kind of how it appears in this explanation, or we could even write it in perhaps the best way, which is like this. Again, all of these expressions are the same due to the nice symmetric property of binomial coefficients. Anyways, quickly running the numbers here to find B4, 3 choose 0 is 1, and B3 is 5. So this is 1 times 5. 3 choose 1 is 3, and B2 is 2, so this is 3 times 2. 3 choose 2 is 3, and B1 is 1, so this is 3 times 1. And 3 choose 3 is 1, and B0 is 1, so this is 1 times 1. In total, we get that B4 is 5 plus 6 plus 3 plus 1, or 15. So coming back to our little table we began with, for n equals 4, a 4-line stanza, the Bell number here, B4, which counts the total number of rhyme schemes, it's 15. There are 15 possibilities. Perhaps now we have the tools to consider the case of the 16-bar rap verse, a classic quantity. How many rhyme schemes are there for this? Well, remember, our formula is a recursive formula. To find B16, we need all the previous Bell numbers as well, and we only have the first handful here. I previously mentioned Ramanujan writing about the Bell numbers before Eric Temple Bell, but even earlier, in the year 1880, in a volume of the American Journal of Mathematics, a fellow named Charles Sanders Peirce had published an article. Well-known logician Bertrand Russell once referred to Charles as the greatest American thinker ever. And in Charles' 1880 publication in the American Journal of Mathematics, there appeared the following triangle. Can you tell how this triangle is constructed? It begins with 1, and then we start the next row with 1, and then add 1 and 1 to get 2. Then start the next row with 2, add 2 and 1 to get 3, add 2 and 3 to get 5, and then start the next row with 5, add 5 and 2 to get 7, 3 and 7 to get 10, and so on. And you may very well recognize the numbers going down the left as well as down the diagonal. What we see is 1, 1, 2, 5, 15, and here in the diagonal we get a sneak peek of the next bell number, B5, which is 52. By continuing to write out rows of this triangle, in which the bell numbers appear both on the left and on the diagonal, we'll be able to find B16 and know once and for all how many ways there are to write a 16-bar rap verse. Now in the past, I trained quite hard in mental arithmetic, so I could carry this on pretty easily quite a while longer. However, I don't want to make any mistakes, and I know eventually it's going to get difficult. So I'm going to bust out my trusty calculator, we'll run these numbers, and I'll get back to you when I'm done. Oh my god. Okay. Alright, I got the answer. It's the number of rhyme schemes for a 16-line verse is oh god. It's let's see here. 10,480,142,000 and 147. So there you go. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the table. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.
Faded.